In this video we'll take a look at a limit as x goes to infinity of this function that's shown here. And I'll take you through a thought process that's typical of wrestling with problems like this. Very often in math presentations you just see the problem and you see a step-by-step solution, but that's not really the way it works. We usually have trials and errors and missteps along the way. So, you know, the fairy tale version is, oh, here's my limit, I know exactly what to do, I just follow some rules or invoke my genius and I end up the answer, which I've designated with an exclamation point there. In reality, I look at the thing I'm starting with and I try to understand it and I try something. I try to get a little further toward the exclamation point. And maybe that doesn't work. Maybe I forgot for the moment that I can't split up a square root by separating it out like this. That just doesn't work. And then I go, oh yeah, okay, I remember this from algebra class. That doesn't work. So put a red line through that approach. So then we try something else. What if I could just somehow ignore that x that's in there, and then I'd have the square root of 9x squared, which is just 3x. So this would all be 3x minus 3x, and the limit would be 0. But that's just wishful thinking, because I can't really ignore that plus x there. It's intriguing enough, though. I mean, there's a little intuition there, so I might try to graph it and see if it does actually turn out to be 0. Does that x matter or not? It's kind of this philosophical question here in my head. So let's graph it. Okay, I think I almost blew up Google there. It says the function may not be plotted correctly. Yeah, no kidding. It's a mess. So I can try Wolfram Alpha. The graph we're looking at here is the blue graph right here. And it looks like this thing looks like a big hockey stick, but it doesn't look like it's 0. You see that the real part's above 0. So now we're pretty sure that this crude business of just forgetting about the plus x and concluding that the limit is equal to 0 doesn't work. So I've crossed that one out too. Now I'm going to erase all this stuff that I know doesn't work. At this point we're reliant on the kinds of algebra tricks and calculus tricks that you've accumulated. One of them is that we can factor things out. So maybe I could just, I can't get rid of this x just by assassinating it, but I could maybe factor out a 9x squared out of the radical and see what happens. So let me try that. So I forcibly removed a 9x squared from under the radical. That leaves me with 1 for the 9x squared I had, plus, and then I've sort of had to contort this x to make it look like a 9x squared so I could take 1 out. And when I did, I have to account for the fact that there's not really a 9 there by dividing by the 9, and not really x squared by dividing by one of the x's. So if you multiply that back through, you get 9x squared plus 9's would cancel, x would cancel, you just be left with x. So, does this help? Well, maybe, because now I can take the 9x squared outside the radical. So let's see what happens there. Well, this looks promising because I've got 3x in common, and the first 3x is multiplied by this bit of radical here. So let me take out the 3x's and see what we get. So here's the 3x that appeared here and here. Those are collected there. Then there's a parentheses, and there's the square root we recognize, and that minus 3x became minus 1. So does this help? Well, as x goes to infinity, 3x goes to infinity, obviously. What we saw in the graph is it looks like it's got a horizontal asymptote. So somehow this stuff here must be keeping the 3x from going to infinity. What a mystery. Let's look inside. The square root's got 1 plus some stuff here with x in the denominator. Now we know 1 over x goes to 0 as x goes to infinity. So everything in the radical inside the square root is going to approach 1 because this part's going to go to 0. I'm going to imagine that by putting a stroke through there. And then we'd have 1 minus 1, which is 0. So this part is going to 0 while the 3x goes to infinity, and we're in kind of a race between 0 and infinity. So we still don't have an answer. One goes to infinity, one goes to 0. We multiply them together. We know that there's a race going on that somehow must result in a tie if it's going to be a horizontal asymptote. But we don't know what that number is. So all of this is very frustrating. I'm going to put this up here as kind of a peg. It's not wrong, it just doesn't get us all the way. So to recap, we've tried two things so far. The first one didn't quite work. We tried eliminating the x, but we realized we changed the... and we must have changed it too much because we get 0 out of that. And then we tried factoring out the 9x squared from the radical, which gets square rooted to become a 3x, and we ended up in a race between infinity and 0. Here's another thing we can try. If we look at this sort of first mistake we made, there is something interesting about it, because we made the function smaller in the process of losing that x, right? So whatever this limit is has to be less than that limit. And maybe we can use the squeeze theorem, where we have a function that's a little bigger and a function that's a little smaller. So even though these two things aren't equal, maybe we can use the fact that this one's a little bigger. So this limit turned out to be 0. And so we know whatever this limit is bigger than 0. That's really not an earth-shattering conclusion, but still it's worth noting. So let's try one more thing. In that vein, if we allow ourselves to alter the function to be a little bigger, how would we want to change the part under the radical to make it nice if we could make it a little bit bigger? Here's one possibility. I'm going to use a red line again because I know I'm actually changing the value of the function. But it would be more convenient if this were 3x squared, or 3x plus 1 squared, which is the same this thing here. In other words, if we square out 3x plus 1, you get 9x squared plus 6x plus 1, and then 9x squared is the same as there. So it's pretty close to the same. It's just a little bigger because here I've got plus x and here I've got plus 6x plus 1. So I've definitely made this function a little bit bigger. But the advantage is, because this is a perfect square, then under the radical I've got 3x plus 1. The squared and the square root undo each other, and I have 3x minus 3x plus 1. So this would say that the limit of our original function has to be less than or equal to 1. This actually does tell us something. Between these two approximations, we know that the limit of the thing we want is between 0 and 1. So that's narrowing it down, but we'd like to get an exact number. So we're going to try another trick. One thing's for sure with this function, it'd be a whole lot easier to deal with if that square root weren't there. And there's a trick in getting rid of square roots in situations like this. That's part of a general bag of tricks in mathematics, where we take something ugly and we run it through some kind of machine, and after the machine's done with it, we get something pretty. In general, this is called a transformation. In this case, what we'd like to find is a transformation that takes this thing that's ugly and turns it into something prettier. So here we go. I'm sure you've seen this algebraic expression where if we take a minus b and multiply it by a plus b, we end up with the two terms back again with the minus sign, but squared. You probably didn't think twice about this in algebra, but this is an interesting way to take something that looks a minus b, like a minus b, run it through this machinery by multiplying by this thing, and getting out something with both of those terms squared. All we've done, if you look from going from the left, if a minus b is our input, then we get a squared minus b squared as our output. So take a look at our problem here. We got this stuff here. Think of that as a, and the one on the right's b. If we had a squared minus b squared, I'd get rid of that ugly square root sign. So this is worth trying. So in our case, if this is a minus b, then a plus b would be the same thing with the plus sign. And I'm going to multiply. But I can't just multiply the top of the fraction by this a plus b transformer. I've also got to multiply the bottom of the fraction so that the whole thing just looks like 1. So again, a minus b, a plus b is going to be equal to a squared, that's the part that was under the square root, now it's escaped the square root, minus b squared, well the b was 3x and it's now squared, so it's 9x squared over the original a plus b. Now you may complain about this and say, yeah, well, you made the top prettier, but you made the bottom uglier. And I would have to plead guilty to that, but just play along with me here and let's see what happens. So here's a map of where we've been so far. Here's the initial problem. We tried bounding it below and got 0, bounding it above and got 1. And then we tried transforming it by factoring out 9x squared and got this form, and then we tried the d square rootinator approach and got this form of it. So the blue ones are exact and the red ones are approximate. The interesting thing about all the exact forms of this is that they pose the problem in different ways. If you look at the original one, you get something going to infinity minus something going to infinity, infinity minus infinity. And in this one we had something going to infinity times something going to 0, infinity times 0. And in this most recent one we have x going to infinity on the top and stuff involving x going to infinity on the bottom. So it's divided here. So it's subtracted, multiplied, divided. All the same problem, looked at in different ways. And this form will turn out to be very productive for us. And in fact, we can use all the ideas we've already accumulated. It's pretty cool. For example, we could try this approximation from above and below trick again with this and see if the squeeze theorem will work. Let's try that first. So if we go back to our original idea and we say, well, I could just simplify this by taking out this plus x. Now that would make this whole denominator smaller by taking out the plus x, but I'm dividing by that number, so it makes the whole fraction bigger. Go through that one more time. If I make the denominator smaller, I make the whole thing bigger. Would you rather have 1/4 of the pi or 1/3 of the pi? 1/3 of the pi would be bigger because I made the denominator smaller. So I took out the bothersome x, and I have to recognize that I made it bigger by using a less than or equal to sign. And this can be simplified now. The square root of 9x squared is 3x. I'll have 3x plus 3x in the bottom, which is 6x. Cancel the x's and I'll get 1/6. So this is an upper bound. That is, the limit, whatever it turns out to be, can't be any bigger than 1/6. Before we knew it couldn't be any bigger than 1. Now we know it can't be any bigger than 1/6. So that's real progress. So what would happen if I tried the other approach and I make this a little bit bigger? If I make the denominator bigger, the whole fraction gets smaller. So in that case, I need the inequality on the other side. We'll do exactly the same thing we did before. We'll turn the 9x squared plus x into 3x plus 1 squared, which is a little bit bigger than 9x squared. It's actually 9x squared plus 6x plus 1, which is definitely bigger than that. And so since it's in the denominator, the whole fraction's smaller. The advantage of that is it's a perfect square, 3x plus 1 squared, which then I can take the square root of and remove it. And we'll have x on the top, 3x plus 1 plus 3x on the bottom, which will again be x over 6x, and then I've got this additional plus 1. So here I've taken the square root off. Now I'll combine term. And because we know how rational functions work when x goes to infinity, we're going to take the x in the top and the 6x in the bottom and ignore the plus 1, and again we'll get 1 over 6. This is an example of the squeeze theorem. We get 1/6 for the lower limit, 1/6 for the upper limit, and so the limit of that as x goes to infinity must be 1/6. So it turned out that these two approximations were useful after all, but only after we had converted the problem into a fraction with the top and the bottom going to infinity. But wait, there's more. We can also use this trick that we employed algebraically up here that didn't work in the original form and try it now in the fractional form. We've already solved the problem. I'm just showing you that we can use this same trick to solve the problem a different way. So we factor 9x squared out of the bottom, and when I bring that 9x squared out of the radical out of the square root, it becomes 3x. There it is. Inside it was 9x squared, and there's the 9x squared plus, and then I had an x, so if I take 9x squared and divide it by 9x, there's the x. So that's all algebraically right. Now I've got 3x times this stuff plus 3x, so it would be nice to combine those two 3x's. So now we gobbled up all the 3x's. That one and that one are pulled out front. We're left with that a radical plus the 1 where the 3x was before. Now the x's will cancel and we'll be left with 1 in the top and a 3 in the bottom plus all this stuff. There's only one x left in this expression. What happens when x goes to infinity? Well, we've got 1 over 9x locally right here, so as x goes to infinity we know that goes to 0. And then inside the radical we've got 1 plus this thing going to 0, so that's just going to go to 1. Plus 1 is 2. 2 times 3 is 6. That's in the denominator, so we get 1/6. And that should give you a warm, fuzzy feeling. In the end, all the work that we did turned out to be useful. We ended up solving the problem 2 different ways, using the squeeze theorem by bounding it from above and below, and by using a factoring method that removed the part that was problematically giving infinity over infinity, and in both cases we got 1/6. As a bonus, that the fractional form of the equation behaves quite well in Google's Grapher, so we can actually create a nice little graph of it. And you can see it looks like it has a horizontal asymptote, and if you look up here at the y values, it's like 0.15, 0.16, something like that. We pull up our calculator, we can calculate 1 divided by 6 and see that it should converge to 1.66 something. So let's see if we zoom way out here, like we're going to infinity. You can see it's starting to get close. 1.658. It's going to take a while. 1.66.